Welcome to our 2022 Lab Roots webinar series. My name is Tara Nilese, Regional Marketing Development Manager for the Life Sciences Electron Microscopy team from Thermo Fisher Scientific, and your host today. We welcome back our returning attendees, and we send a big hello to our new attendees wherever you are in the world. We are pleased to have two very engaging speakers lined up for our session today. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. Now, let me introduce our speakers. Melissa Chambers is a director of the Center for Structural Biology Cryo-EM Facility at Vanderbilt University. Melissa has 15 years of experience using cryo-EM as a tool for investigating structural and functional organization of protein complexes. She has managed 4 facilities, including 2 at Harvard Medical School, and trained 200 plus researchers in molecular electron microscopy applications. While her primary expertise lies in single particle analysis, she is eager to explore the emerging techniques of in situ cryo-electron tomography and micro-ED and aid researchers in applying these in fields beyond structural biology. Every day, Melissa works to help others understand the challenging topics and master difficult skills in cryo-EM. Certainly a noble effort and endeavor. And also with us is Dr. Natalia de Val, who is a biochemist and protein engineering specialist with more than 15 years experience in single particle cryo-electron microscopy, as well as immunogenic design efforts for vaccine achievement. She completed her master's in biochemistry from the University of Zaragoza in Spain, and she received her doctoral degree in biochemistry from the University of Leuven, Belgium. In October of 2017, she joined NCI as the director of the Electron Microscopy Laboratory and the team lead for Cryo-Electron Microscopy section at the Center for Molecular Microscopy. She was responsible for the management of a wide portfolio of projects related mainly to cancer and HIV diseases. She has authored over 70 scientific publications and in high-impact scientific journals such as Science and Nature. She joined Thermo Fisher Scientific in January 2021 as a senior scientist, senior product specialist for electron microscopy. In her current position, she is supporting electron microscopy in the East Coast and Midwest of the USA. In the first part of today's session, Melissa will share more information on how cryo-EM is being used to gain important insights into fields such as structural biology, biochemistry, and structure-based drug design, and also share her experiences on how anyone can get started. In the second portion of this event, Natalia will give us details on the factors to consider in instrumentation for a new facility. And now we're ready to learn more from our speakers. Melissa, over to you for your presentation.
Thank you, Tara. I'm excited to kick off the first of this series, Getting Started in Cryo-EM, with a talk today on recent discoveries in structural biology, biochemistry, and cell biology. Cryo-EM is a method for investigating biological structures and utilizing cryo-ET and cryo-EM that can provide a wide range of resolution information all the way down close to 1 angstrom. This is used to investigate how molecular machines work, drugs bind targets, proteins interact, and complexes integrate in a cellular context. Vitrification allows for imaging samples in the near native state. The process of vitrification happens when an aqueous sample is frozen so quickly that ice crystals do not form, and it allows us to image it in the transmission electron microscope without limiting the resolution of the sample. Computational methods are then used to reconstruct this into 3 dimensions to learn a variety of information about purified proteins, biomolecules, or cells. The main limitation for this method is that samples smaller than 100 kilodaltons in molecular weight are challenging, but not impossible. This allows us to study a variety of samples, such as membrane-bound proteins and soluble proteins, large viruses, liposomes, supramolecular complexes, and even small enzymes and nucleic acids. The popularity of cryo-EM as a method for studying protein structure has grown, according to unique structures deposited in the protein data bank. In 1991, there was only one unique structure deposited that year, and last year there were almost 3,000. So highlighting some of the recent discoveries, I'm going to start with this calcium-activated chloride channels, which are involved in the physiology of the eye and are genetically linked to retinal degenerative disorders and progressive vision loss. Human BEST1 and BEST2 were studied by this group in multiple conformations from an open state, and a partially open state, and a closed state. And they were able to determine these structures to the best resolution of 1.8 angstroms. This allowed this group to understand how channel functions and to study specific mutants. Time-resolved cryo-EM aims to study processes on a millisecond timescale and looking at conformational changes during assembly and disassembly of protein complexes. In this case, this group was looking at actomyosin in combination with ATP. They used a microfluidic device to mix the sample just prior to spraying it on an EM grid, and then immediately plunged into liquid ethane for vitrification. And here they were able to follow this process from 7 milliseconds all the way to 640 milliseconds. Cryo-EM can be used in combination with other structural and analytical methods. While I mentioned that cryo-EM has a main limitation of being more difficult to study proteins with a molecular weight lower than 100 kilodaltons, NMR is very well suited for samples below 40 kilodaltons. And so these groups combined these two approaches to study a large dodecameric enzyme, TET2, which is 468 kilodaltons. This mixed approach allowed them to use a 4.1 angstrom resolution cryo-EM map combined with NMR assignments from the 39 kilodalton subunits to refine the model to a resolution of 1 angstrom. Several groups, including these groups from University of Oxford, along with Thermo Fisher Scientific, are working on utilizing mass spectrometry to filter the purified protein sample to apply that high purity sample to the TEM grid before vitrification. The hopes of this work is to make high resolution structure determination by cryo-EM more efficient by optimizing the sample that's on the grid. Some exciting work on how cryo-EM can be used to investigate human health. The Hibbs group at UT Southwest Medical Center investigated antibodies from an encephalitis patient and how these directly inhibited the GABA-A receptor function. One antibody directly competes with the binding of neurotransmitters, and another antibody targeted the subunit interface where compounds used to treat seizures interact with the receptor. These identified residues in these antibodies are involved in specifically define the mechanism of this autoimmune encephalitis. Stepping away from purified protein and looking into this in situ work, which is where you can image complexes in cells that have been vitrified on a TEM grid. Here you can see that cells were grown on a TEM grid, put into an electron microscope and imaged. And some virus assembly is well understood, but this is not the case for the family of alpha viruses. Chikungunya virus is the most common alpha virus that affects humans, and there's no known vaccine or antiviral available. So using cryo-electron tomography, infected human cells were vitrified and imaged to determine structures of viral assembly intermediates to inform how this viral assembly occurs in the cell and how the budding can be blocked by antibodies. Another example of in situ work combines techniques from single particle analysis with tomography and sub-tomogram averaging. Studying ribosome maturation has large small units and small subunits of the ribosome are synthesized independently in the nucleolus before being exported to the cytoplasm, where they assemble into functional ribosomes. And so in this work of imaging the nucleolus and identifying different categories of ribosome subunits, it refined That the small subunit did some subtomogram averaging, and the small subunit class averages show a rearrangement of domains to become more compact before it's being exported to the cytoplasm. And this allowed the group to develop a model for ribosome maturation and how the phase separation of the nucleolus supports ribosome biogenesis. As exciting as cryo-EM is, there's always new developments and technologies coming forward. This first one is from Chris Russo's group, and they present a process for manufacturing a new type of TEM support grid that has small hexagonal holes instead of the commonly used round holes. And they have shown that this reduces specimen movement during imaging, which can help improve high-resolution information. And this method also shows how you can produce these grids yourself in-house with the right equipment. Dono's group is developing methods for making in situ tomography imaging more high throughput. Cryo-EM is the preferred technique for studying complexes larger than 100 kilodalton and in near native conditions. Samples can be purified proteins, viruses, biomolecules, and intact cells. Studies can reveal how ions move across membranes, biological processes progress with time, viruses infect cells, and antibodies affect human health, and how our basic understanding of cell biology may change as we study these processes in native environments. There are always new innovations coming out that are broadening the applications of cryo-EM and expanding the accessibility to researchers. So that's the end of this first section on getting started in cryo-EM. So in this section of getting started in cryo-EM, I'm going to discuss some workflow considerations. There are three main methods to reveal structural information of biological molecules. The first is X-ray crystallography. In this method, samples must be crystallized, which means they're removed from the native or experimental environment. This step is not trivial and can take a lot of time and effort. Crystals reveal a static form of a complex, and it's not dynamic. It requires a large amount of sample at high concentrations, and it can yield very high resolution data. NMR is able to examine samples in an aqueous solution in a near-native state. It is good for studying dynamic and flexible complexes. A large amount is required of 300 microliters or more. And if this is, while there are some techniques that can study higher molecular weight proteins, in general, a small molecular weight of 40 kilodaltons or less is ideal for NMR. The sample needs to be very pure, and it can yield high resolution data. So we're here to talk about cryo-electron microscopy today and the great things that this technique can do. So the step of vitrification of your samples maintains your samples in a near native and experimental state. It's suitable to investigate complexes with multiple conformations and can accommodate some amount of heterogeneity and flexibility. You only need a small amount of sample. 20 microliters of a 1 milligram per milliliter concentration is enough to repair several grids. It can be difficult to work with complexes lower than 100 kilodaltons, but it is possible, and there are new techniques that are pushing this limit. It is possible to get below 2 angstrom with ideal sample and optimization, while 2 angstroms to 5 angstroms is more common, and also in that range, a lot of biological questions can be answered. As exciting as cryo-EM is, biochemistry is still the most important step in the process. Size exclusion chromatography should be one of your last steps of purification. In this project with HERD1, HERD3 complex, we had this nice peak that gave us confidence that our sample was biochemically pure and structurally homogeneous. You can see that here in this cryo-EM image and the 2D class averages that resulted from it. While some amount of flexibility and conformational changes can be analyzed by cryo-EM, it's best to minimize these if possible. It's rare that you need to change your buffer from your experimental conditions. You do want to keep salt to a minimum, as that can have a high background in your cryo-EM images, and minimize the amount of glycerol, preferably no glycerol at all. I have never had the luxury of being able to work with a sample that I could purify and then freeze to later thaw and use for cryo-EM. And often a fresh purification needs to be performed before vitrifying grids to ensure stability and homogeneity of your complex. Negative stain analysis can really help with your assessment of your sample for cryo-EM. It's excellent for informing the suitability based on oligomerization state, domain organization, binding sites. This can help you ensure that your particles are homogeneous in size, shape, and conformation. This can also help you change buffer conditions or purification conditions to reduce aggregation, heterogeneity, degradation, or perhaps using a component in the buffer that leaves artifacts. And this is a quick and efficient way of screening purification conditions and buffer components. So here's an ideal image of protein complexes in negative stain. You see a very similar size and shape of these complexes, but beyond just a single image, you can do some 2D classification that can reveal more information. The resolution here is limited to about 18 angstroms, but it can help provide quantitative evidence for homogeneity and suitability for continuing with cryo-EM. Here we see a top view of the complex and a side view. If this isn't the case, and you don't have nice 2D class averages, this is the chance to back up, change your experimental parameters, and repeat. A lot of work up front on your purification and optimizing your sample before going into cryo-EM is going to save you a lot of effort down the road. So I want to show some examples of how the same particle can look under different conditions. So this is a negative stain image of the proteasome, about 750 kilodalton, so it's a large complex. Here's an image of it in vitrified ice. Not as high contrast, but you can still see these complexes and they're nicely dispersed. And then in an in situ environment. So this is in a whole cell that has been vitrified, and you see these proteasome complexes in their native state. You can see some indicated by these yellow arrows. You have side views, you have top views. And a little more detail, you can see them here. So it's really fascinating, the scale that you can look at these complexes on. When it comes to vitrification, there are some considerations to think of. While this can preserve your sample in a near native condition, with no artifacts from a stain and no limit to your resolution, it also is low contrast and can be tedious and not always reproducible when you're first starting. So here we have a cryo-EM grid. It has a metal support mesh, and on top of that mesh is a Holy film. And in these holes, you can see the side view here, this is where your vitrified ice will be. That will have your particles in it. So there are a variety of grids and substrates to use. The metal support mesh here can be copper or gold. There's a range of mesh size from 200 to 400. While 400 is very robust and easy to handle, it has smaller areas for imaging. And on the opposite end, 200 has very large squares for imaging, so that can increase your exposure rate when you're collecting data. It can also be very fragile. So a 300 support mesh is a good compromise. The Holy film on top can also be made of carbon or gold. There's evidence out there that using gold, both the support mesh and the film, can reduce specimen movement during imaging. There's also graphene oxide support that can be laid over on top of this film that provides support for your samples to encourage them to get into the holes of ice. In B here, this is ideally what you want. On the side view, you can see you have particles in random orientations, fully embedded in the ice. C and D have particles on the surface of the ice, and that's called the air-water interface. And that can either induce preferred orientation, such as in C, or even damage the particles in D. In figure E and G, these both can be assessed with some negative stain. So in E, you have degradation of the complex falling apart, and in G, you have aggregation. And doing a lot of work with negative stain may help prevent this from happening. In F, this is where your particles prefer to stick to the carbon instead of being embedded in the ice. So a way to get around this is to maybe try gold film or even a graphene oxide support. Vitrification is the bottleneck of this workflow. My suggestion is to plan your vitrification steps very well to make each attempt more successful. Follow your processes in the same order. Try to have the same timing between steps so that everything can be more producible when you do it again. Your goal is the thinnest ice where you can still visualize your particles. And this may not be the same for every sample you look at because everything can be a little different. Several rounds of screening, preparing more grids, doing some cryo-EM screening, processing some data, going back, that is not uncommon. In the end, it may only be one grid that you need to have enough areas to collect images to get your high resolution information. There's a lot of innovation in this area with new grid types, new manufacturing, homemade vitrification devices. So there's going to be a lot of movement in the area of vitrification in the future. So some key points I want you to take home is that biochemistry is the most important step. All the optimization of your sample before moving on to vitrification is very important and it will pay off. Vitrification is the bottleneck of this workflow and it will take a lot of effort. Be open to embracing new innovations and new technologies that will help. There are a lot of resources out there, but if I could point you to one place, it would be cryoemcenters.org, which is the NIH's national facilities for cryo-EM, cryo-ET, and curriculum development. They have excellent courses to follow and information to help you get started. The 3D EM mailing list can be considered a community resource where it's a great place for you to ask questions of people in the field, stay up to date on topics, learn about meetings and workshops, and even job postings. And finally, there's a collection of bad cryo-EM images from the Electron Microscopy Center at New York Structural Biology Center. These images are categorized, and so as you are struggling to get very nice vitrified ice or good images, you can look at the images there, see if you can help diagnose what's going on with your samples and some suggestions to fix them. So that's the end of this section, and I'm going to pass it on to Natalia, who's going to talk about infrastructure and instrumentation to help you get started. Thank you.
So thank you, Melissa, for that amazing presentation highlighting all the beauties of cryo-EM. So before I start my presentation, I would like to again, explain very quickly how cryo-EM is becoming a very important and key technique for structural biology studies and is the fastest growing structural biology method for characterizing proteins and pathogens. And it's very important because, as you know, the human body contains between 80K and 400K proteins. So being able to understand how these proteins interact with each other are essential for, understanding diseases and being able to develop new therapies. So this is an example of how cryo-EM was very, very important and key for 3 different diseases. The first one I want to highlight today is the new tauopathy that was discovered in the MRC lab by the UK people. So we were able to, using cryo-EM, to really understand and discover a new disease. In this case, the TLNT for Alzheimer's. So thanks to cryo-EM, we were able to understand better this kind of diseases. Similar with Ebola, using cryo-EM, we were able to discover 2 new antibodies that they were able to bind to 2 Ebola viruses, the Ebola one and the Sudan one. And this is are the biggest and deadliest outbreaks viruses. So this is very, very important to understand how we can target these viruses. And finally, cryo-EM is helping a lot to understand as well cancer formation. So this work was done at Stanford, and we were able to, for the first time, get a cryo-EM structure of this kinase enzyme. And it was very important because we were able to see how we can target this enzyme to develop new therapies. With that being said, you already know, how important cryo-EM is, and I want to highlight some of the main, I will say, state of the art, like we were able to obtain with CryoEM. So the first one you can see here in your left is the best resolution. In 2020, the first atomic resolution coming from single particle analysis was done at 1.22 angstroms. This is apoferritin, and you can see water molecules, so oxygen and hydrogen atoms. So it's very impressive because, you know, I never thought when I started doing cryo-electron microscopy over 15 years ago, like I will be able to see this kind of atomic resolution maps coming from CryoEM. So it's very impressive. Obviously, we were able to analyze the largest viral protein, over 10.1 megadaltons for this poliovirus type 1, doing CryoEM. And this was done by cryotomography, and the resolution was 2.9 angstroms. And obviously, we were able to as well obtain the smallest protein, like around 40 kilodalton, like for CryoEM single particle standards is very, very small, at 3.7 angstroms. So again, only to give you an idea how important CryoEM is, and is even becoming more and more essential to do CryoEM if you want to analyze your protein or complex of interest and have structural biology information. So again, some people still think like CryoEM is, you know, a very difficult technology, it's a complex technology, it's still very expensive, and it's difficult to access and difficult to use. But I'm hoping with this seminar series, you will be able to get the point like it's not the case anymore. We are trying to make this technique as affordable as possible, to open CryoEM to other people, to many labs. We are trying to integrate artificial intelligence and machine learning, like can make the use of the microscopes much easier. And obviously, we are trying to provide as many trainings and workshops and hands-on as possible, like people can, you know, understand the technique and can become experts in CryoEM. So this is a tiny video, like I want to show you very, you know, quickly the differences in between the two main CryoEM techniques. One is single particle analysis, so from proteins in solution to atomic model, is ex situ technique. So you have your protein of interest, express and purify it. You vitrify the protein of interest into the CryoEM grid, and you load that CryoEM grid into your TEM microscope. And this is a typical image you will be able to obtain under CryoEM conditions. So computationally, when the data is collected, you will be able to pick up single particles in different orientations. So you will be able to get bottom views, side views, and in between of your particle of interest. So the more orientations you will be able to get of your protein, the better, because you will be able to create and generate the thing that we call the 2D projections or 2D classes. Like they are projections of your particle of interest. And again, computationally, you will be able to extract the information you need from those 2D projections to generate at the end the 3D reconstruction of your protein. So this is the typical ex situ work for single particle analysis. And as I said before, with the new cameras, the new hardware, we really can reach atomic resolutions almost on regular basis, sample dependent. So this is the typical workflow that you will be able to get: sample preparation, data collection, and 3D reconstruction. And I will explain later on during my presentation all the instrumentations and all the materials that you will need to think to be able to do a single particle analysis in your lab. Cryotomography is being able to see protein in cells and tissues, so it's in situ work. And in this particular video, I would like to show you a tiny bit how it works, mostly focusing on viruses. So you have your virus of interest, and you will be able to vitrify this virus in your CryoEM grid. And after that, when the virus is in the grid, you will be able to load that grid into the TEM microscope. The main difference in between cryotomography and single particle, or one of the main difference, is the way you collect data. So for single particle, you don't do any tilt. For cryotomography, you are doing a tilt series. So you are collecting data in between -60, -70 to +60, +70 degrees. So you are generating this tomogram, like we call it like a movie, where you put together all the tilt series to create the tomogram of the virus or the tomogram of the cell and protein of interest in situ. So again, computationally, once this tomogram is collected, you will be able to do analysis on the tomogram, and we can call this tomogram and subtomogram averaging, where you will be able to do as well some segmentation work to obtain the 3D volume of your final virus. So the resolution is different. You can get atomic resolutions with single particle. You can get around nanometer resolutions with tomography. But the beauty of tomography is like this work in situ. So you can really understand, how the proteins are interacting with other proteins in the context of the cell. So the process and the pipeline for tomography is a bit different, like for single particle analysis. So the first step will be vitrification of the cells or the virus of interest. You can do some correlative microscopy as well, so you can target and label the protein of interest with a fluorophore, and you can localize that with an external cleanse system. You can go to the focus ion beam to do a lamella, so that means you can open cells or you can open windows into the cell, so you will be able to create the lamella. Like they are very thin, in between 150 and 250 nanometers, to literally load those lamellas into the transmission electron microscope to start collecting data in the cell. Why we need to do the focus ion beam when you are working with cells? This is very important step, because otherwise the cells are too thick, and if you grow the cell directly into the cryo-EM grid and you transfer that grid directly into the transmission electron microscope, you won't be able to see anything because it's too thick. So that's the reason you need to open those windows in the cell to be able to see all the organelles and all the protein of interest internally in the cell directly by transmission electron microscope. So this step is very important for tomography and is not necessary for single particle analysis. So the single particle analysis workflow, I have, several steps here, and I want to highlight first how Thermo Fisher is really working very, very, very hard to do the full pipeline for single particle analysis as easy and as affordable as possible for even novice people, like they are no expert yet in cryo-EM. So the first step, obviously, is always sample purification. So Thermo Fisher is here as well to help you in that step. You have different, machines, different instrumentations, like you will need to purchase to be able to express and purify the protein of interest. And I highlight some examples here. For example, the electrophoresis systems, the gel imaging system, the gel hand transponder, all the FPLC, SPLC machines to be able to purify the proteins, and obviously all the pipettes and micropipettes to do all that. The second step, obviously, once the sample is already purified, is going to be the sample quality control. And that can be done very easily with transmission electron microscopes, like can be the side entry holders, like the Talos 120C or the Talos 200, or can be the new entry-level single particle analysis microscope, or new Tundra at 100 kV. So you will be able to express, purify your sample, put the sample in a cryo-EM grid or a negative stain grid, room temperature first, screen the quality of the sample. So that means if the sample is homogeneous, if the sample is heterogeneous, if it's aggregating, and using those microscopes. While the sample is good by room temperature standards, you will be able to do the vitrification process. And for that, you will be able to use the VitriBot coming from Thermo Fisher as well. So it's a very easy machine for vitrification purposes. And again, you will need as well different tweezers, different pipettes, and as well as, cryo-EM storage dewars. So once you have your sample vitrified, you will need to be able to store those samples, and again, using different devices and dewars for sample storage. And finally, you will be able to use the glacios and the cryos, the very high-level TEM microscopes, to be able to do data analysis and data collection. And obviously, when data is collected after using the glacios and the cryos, you need to transfer the data into a cluster where you will be able to do all the data processing using Relion, Cryospar, and other programs for single particle analysis. So again, sample purification process, sample quality control, mostly for room temperature, negative stain, single particle analysis. Once the control is good, you will do the vitrification in the VitroBot and the storage and visualization in the glacios, cryos, and data analysis. So I put together a table, several tables, I will say, with highlighting the main instrumentation that you will need to establish an electron microscopy lab. And this is the general instrumentation like you will need for single particle as well as for tomography analysis or studies. So here in the column, here in the left, you can see the device. In the middle, you can see the purpose, and obviously the supplier like we recommend. So the first thing, obviously, you will need to have is a microscope, and I didn't even add that into this table because it's obvious. You will need to have a transmission electron microscope. You can get one for screening and optimization and the same one for data collection. Or if you are lucky enough and you have, the capability enough, you will get two. You will get one entry-level microscope for screening and optimization purposes, and a second microscope can be a glacios, can be a cryos for data collection, for high-resolution data collection, and for tomography data collection as well. So that's obvious. But plus, except for the microscope, like obviously, you need that, you will need to have a VitroBot. That's for vitrification of the grids. And you will need to have a plasma cleaner or glow discharger. Like it's very important to provide hydrophilicity of EM grids to optimize the distribution of the particles on ice. You will need to have a carbon evaporator as well. This can be optional, but we highly recommend it for providing an additional carbon layer into the mostly the negative stain EM grids for screening and optimization of your samples. You will need a polarization optical microscope for ensuring that the autogrids are properly clipped into the autolader cartridge. You will need to get several dewars. The first dewars, 4 liters ones, they are for easy nitrogen pouring when you are vitrifying the grids. And the very big ones, the 120 liters tank, those are for liquid nitrogen storage. So you will need to have those for storage and for pouring nitrogen. You will have to get access to a cabinet for ETAN, including installation and connection to the exhaust. This is very, very important because for safety reasons, you need to have the ETAN in that cabinet, or the ETAN can be as well stored under the chemical hood. You will need to buy ETAN gas cylinders, and this is, we need ETAN for vitrification purposes. So usually we recommend a ETAN cylinder of 20 liters, but you can decide which one you want to buy. Obviously, you need to have a storage dewar Taylor HC35, and this is for long-term storage of vitrified grids. Once the grids with a sample of interest are vitrified, you can store them for months or even longer if you want, before data collection in the microscope. But for that, you need a specific, a dewar, like it's very, very big for data storage. The grid storage system, obviously, you need to store the grids in a very organized way. So we recommend this system, like they are very compatible with the HC35. And obviously, the grid storage POC, like they are very convenient to store those grids in a very, very organized way. You have a need for a foam dewar to transfer those vitrified grids into the box. You will need as well the Taylor Wharton dry zipper if you want to ship the grids to other facilities. For example, some cases you have in your lab a screening microscope to optimize and to screen the grids, but you don't have, the cryos or the glaciers to collect data. So you need to ship those grids to other national centers. So this will be very useful for that. You will need a digital dry bath, with blow heater. This is very convenient for dry cryo tools during the clipping and the loading of the grids. Obviously, you need pipettes and a drying cabinet to accelerate the drying process for a small tooling. And all those accessories here, I don't want to go one by one through them, but this will be provided by Thermo once you have the microscope delivery. And they are totally necessary for clipping the grids and prepare the grids to go with the glaciers, the tundra, or the cryos. The last thing, obviously, more consumables. You need to think always about the consumables, that they will be very important to run the microscopes, and as well, processing PC. So obviously, I explained a lot all the materials that you will need to prepare the sample, to prepare, and purify the protein, to, screen the samples in different microscopes, but and how to collect data collection. But the only thing you don't want to forget is that you need to process all the data you are collecting. And for that, you need to have a specific PC for doing all the data processing. And in that regard, you need to be able to head some Linux box stations, like they are or can be individual for your lab, but you will need as well to have access to the cluster in your institution. Like you will be able to not only process the data in the cluster with different softwares like Reliant or CryoSpark, but as well being able to storage those data, because they are very big in the archiving area of the cluster. So this is something that you need to keep in mind. You need to be able to have access to a big cluster to process the data and storage the data, and even using Globus or their system to transfer data to collaborators as well. So being careful that you need to be to have some kind of very IT support. This is very important. Obviously, you need staff to be able to run the microscopes, to be able to prepare the samples for screening and optimization of the samples. And obviously, you need to have some IT person or have some contact with IT person in your institution, like can help you with data transfer and data processing as well. And we have, obviously, Thermo Fisher is here to help you as much as we can. So we have applications or apps, an online system, so you can get over 50 hours of single particle analysis workflow education. We are working as well on putting cryo-ET workflow as well in this website. You can get cryo-EM school access, in-depth 40 question exams, and you can even get a certificate of completion after that. And we have some customers here, a testimonial, like they are very, very happy with this, system. Obviously, we encourage you to please join our cryo-EM learning community today. Don't delay this, because you will be able to get access to webinars, podcasts, videos, question and answers, even ask the experts sessions, and reach out to the go online thermofisher.com cryo-EM, and you will be able to find all these things to be able to learn even more what needs to be done to start a cryo-EM lab. And with that, I would like to thank you for your attention and your time today. And please don't hesitate, if you have any extra questions, to reach out to me. This is my email address, natalia.deval@thermofisher.com. Thank you so much.
Wonderful. Fantastic presentations, Melissa and Natalia. Thank you so much. Really a lot of valuable and practical information to help people get started on their journey through cryo-EM. It's great to see all of these tips and valuable content. Now it's time for our question and answer session, and I'll remind the audience to please type in your questions and click submit. We already have some really good questions coming through. We've got a fantastic audience of various user levels. So I will go ahead and start the first question. Let's see. This question is for you, Melissa. About how long does it take to get familiar with the sample preparation processes?
Well, I think one thing about this technique is that you get out of it what you put in. So if you spend a lot of effort attempting to handling these grids, working with the vitrification process, making sure you have a nice protocol that you can consistently follow every time, that will go very far and benefit you. Oftentimes, for projects like this, someone may, spend a lot of effort, get good grids, then they may spend 6 months or more collecting data, processing data, and then when they're ready to come back to it, it can be some time. So it's always good to have a really nice protocol written out that you can come back to. But the more experience you have handling grids and vitrifying grids and screening them to get feedback on the vitrification conditions, to do it more reproducibly.
Excellent, thank you. And maybe this one is a good one for you, Natalia. What type of training support is included when you purchase a microscope?
Okay, that's a very good question. There is no straightforward answer. Depending, we have different, I would say, programs, different package that you can purchase with the instrument. So depending of your expertise, we will recommend you to purchase one or another. So you can totally decide how many hours. It's very flexible. All these packages are very flexible. For example, if one package, let's say package A, comes with 30 hours of training, and this can be on-site training with our, application scientist specialists, or this can be virtual training as well. So once you are done with the 30 hours of training and you don't feel still confident enough to use the microscope by yourself, you can always request to have more training sessions. And again, we have as well a support, like it's a virtual support, like it's 24/7. So if you have any issues with the microscope or any problems with the software or any question, you can always reach out to us through that program and we can help you. So it's very flexible, and depending on your expertise, we will recommend you to purchase one package or another package. But we are always here to help you, and support you during your journey on adopting Cryo-EM.
Perfect. Thank you, Natalia. All right. And maybe here's one, maybe Melissa, if you'd like to start off, maybe Natalia can also jump in after. So if during vitrification, a complex falls apart, what can be done to avoid it or to fix it? Melissa?
So the first thing I would suggest is, and I mentioned this in my talk as well, check it by negative stain right before you vitrify it. Even if this is a purification you do frequently all the time, you probably also know that sometimes things can go wrong. So make sure that the protein is intact before you vitrify it every time. If it's then still falling apart, maybe consider some buffer conditions. If it's a membrane protein or you use different detergents. I've seen different detergents work better for vitrification for some complexes than others. You can try, if it's maybe sticking to the edges of the grid holes, you can, if you have a carbon foil, you can try some maybe with a gold foil. It could also be potentially maybe you need a little bit thicker ice. Everybody wants to go for really nice thin ice, but sometimes thin ice can be too thin for your samples. So it can be just kind of varying not only your experimental conditions, your buffer conditions, but maybe also some of the grid substrates. Natalia, do you have anything to comment on that too?
Yeah, no, that's perfect. I think you already touched every single point. Another thing maybe I can add is maybe try to change, the substrate. Even sometimes this can help. Instead of using the typical carbon grids, you can use gold grids or maybe some kind of affinity grids. So there are plenty right now in the market, like they can sometimes help with this kind of problems. And again, it's not a magic recipe. Depending on the sample, you will need to try different approaches. But I completely agree with Melissa. Those are the main things that you can try when something is falling apart.
Wonderful. Very, very good practical information. Really avoiding those pitfalls and getting closer to excellent data. Okay, the next question that we have is a detailed question. And maybe, again, Melissa, if you'd like to start us off. Great work. How will cryo-electron microscopy help in teasing out the pathophysiology as well as therapeutic design of neuropsychiatric disorders, namely autism spectrum disorders, dementia, obsessive compulsive disorders, and schizophrenia? And maybe let's focus on the dementia group of disorders, abnormal accumulation of proteins in neurons. So Melissa, how is cryo-EM used for neurodegenerative applications?
Yeah, those are some really great things that can be investigated. There is a Shore Shares group, and Natalia touched on this in her presentation, has done a lot of work on assembly of tau filaments and looking at mutants that are common in Alzheimer's disease, and also assembly similar to chronic traumatic encephalopathy. And so there are groups that are working on that specifically, and that's more of a single particle approach. In general, looking at, maybe if you're looking at different types of cell interactions, that can be something leading a little more towards using some cryo-ET and some in situ work. I know some groups that work on synaptic vesicle release in neurons, and neurons are thin enough that you don't have to mill them with the FIB. And so you can grow those cells on grids and put them in the TEM and image them that way. But you could also look at different cell types coming together or different interactions in a cell, cell migrations, and looking at using the FIB to thin those.
Perfect. Thank you. And Natalia, anything to add?
No, I think as Melissa pointed out already, we have plenty of examples of different investigators working with this kind of diseases. And at the beginning, a few years ago, they were very challenging to study, because they are filaments, they can be very random, they can be quite flexible. I mean, all the things like they are very challenging for crystallography, for example, or even for cryo-EM single particle analysis. And right now, another thing like is always very impressive to me is like with the new hardware, the new cameras, the new software, the way we analyze the data, even the way we prepare the samples, is getting there, is helping us a lot to be able to study these very challenging, diseases. And as Melissa said, we have plenty of examples of, investigators doing that. Mostly, one of the ones that we highlight during the talk today was Source in the UK, is focusing his lab in this kind of diseases. And it's very exciting to see how cryo-EM is helping, cryotomography and single particle in analyzing and developing even new therapeutics for these diseases. So it's a perfect moment to jump into cryo-EM if you really want to study these kind of diseases. That will be my recommendation.
Perfect. Thank you both. And I'll just make sure that we highlight, please explore the resources tab where you could find some of the links and web pages that Natalia and Melissa just referenced. On our web pages, we've got learning centers, and we even have a webinar of past tau filament cryo-EM exploration. So please make sure that you explore those resources for additional information. The next question, Natalia, let's have you start off with. How challenging is it to capture in vitro dynamic processes such as polymerization, for example, using cryo-EM?
Yeah, that's a very good question. So these kind of dynamic processes, they are still they are very difficult to do by crystallography, for example, because we can, in general, think it's more like a static technique, so you have usually one state of the protein that you can crystallize, and usually to do or to have those crystals, you probably need to do some kind of modifications in your protein of interest. So cryo-EM, the beauty, mostly single particle, for example, is that you can really work with very close native, protein states, and you can even capture different conformations of the same protein. And again, we are developing methods on how to even capture much more small changes in the protein, like it's almost live visualization, and more APIs and investigators are trying to do this, because already by cryo-EM you can be enabled, and one example is the ABC transporters. For example, you can get the closed state 100%, you can get a 100% open state, but you have plenty of different conformations and states in between open and closed. So those can be totally captured already by cryo-EM single particle analysis. And it's very easy to do in the sense that you can, collect the data, do the data processing and analysis, and you will be able directly in the 2D projections or 2D classes to see the differences, in between those states and generate different 3D volumes using those 2D projections with the different states. Different people, as Joachim Frank in Columbia and other people, are trying to develop techniques to even capture and freeze in nanoseconds, a specific conformation of, for example, an enzyme. So this can be already be done, and it's having more and more developed, to be able to capture all those dynamic processes, the best we can. Again, it's not an easy task, but it can be done.
Perfect. Thank you very much. And we'll just answer one last question in the last minute or so. Does the tomography need to be captured in real time, or can it be retrieved later, and can the image be rotated? So if you just have a 1 minute answer for that, please. Natalia?
Yeah, I can go ahead. So I will probably say the tomography, you can do all the data collection of the tomography live. Once you prepare, for example, the lamella on your cell, those lamella can be safe for, several weeks or months if you want in liquid nitrogen before going to the TEM for data collection. We highly recommend to prepare the lamella, and the sooner you can, to do the data collection in the microscope to avoid any ice contamination. The lamella can be quite fragile sometimes, specifically the thinner you make the lamella, the more fragile they can be. So once you have the lamella, for example, you can go to the TEM, collect data there, and make the tomograms. And once you have the tomograms, you can do all the data processing. And that can be done wherever you have the time. So it can be live, you can collect data and directly start doing some data processing in the tomogram with the TIL series, or you can collect the whole data and do the data processing later on. So I hope I answered your question in there.
Yes, great. Thank you very much. So before we go, I'd like to thank everybody for joining us today and for all of the interesting questions. The questions that we did not have time for today will be addressed via the contact information that you provided at the time of registration. All of this information, as well as others in our electron microscopy series, can be viewed on demand on LabRoots. We encourage you to share this session with your colleagues who may have missed today's live event. If you'd like to learn more about getting started in cryo-EM, please visit our website to explore all of the learning resources to support your cryo-EM endeavors. You could find out what's possible in this exciting field or contact us here if you have additional questions. I'd like to send a huge thank you to our speakers, Melissa and Natalia. You shared so much valuable information. I hope this really benefits people looking to get started, and they've got a good set of references to help them along their way. And thank you to everybody who joined us today and our organizers. Until next time, goodbye. Thank you.